Bismillahirrahmanirrahim. Assalamualaikum and hi everyone. This lecture 3 is the continuation from Parallel Computing Platform Part 1. So let's start. Okay, so physical organization of parallel platform actually is taken from the parallel machine called Parallel Random Access Machine or PRAM. The architecture of an ideal parallel computer, a natural extension of the random access machine serial architecture, is the parallel random access machine or PRAM. So PRAM actually consists of two components: processors is represented as P and a global memory of unbounded size that is uniformly accessible to all processors. So processors share a common clock but may execute different instructions in each cycle. Alright, so the PRAM can be divided into four subclasses: exclusive read, exclusive write, also known as EREW, two concurrent read and exclusive write, CREW, 3 exclusive read concurrent write ERCW, and 4 concurrent read and concurrent write CRCW. Okay, what does concurrent write mean anyway? So there are four things or four tasks to be considered. The first one is common. So it is common, write only if all values are identical. Arbitrary, write the data from a randomly selected processor. Look at the priority, follow a predetermined priority order. And last one, sum, write the sum of all data items. Okay, so processors and memories are connected via switches. So since these switches must operate in O1 time at the level of word, for a system of P processors and M words, the switch complexity can be measured by O M multiplied with P. So clearly, for meaningful values of P and M, a true PRAM is not realizable. So we cannot really know the exact numbers of PRAM values. So this is just an estimation of the number of switch complexity that we can use to construct the parallel computer. Okay, so next one. So to communicate between processors and memories, so it needs interconnection networks. Interconnection networks carry data between processors and memory. So it's made from switches and links such as wires, fiber. Okay, interconnects are classified as static or dynamic. So static networks consist of point-to-point communication links among processing nodes and are also referred as direct network. Meanwhile, dynamic networks are built using switches and communication link. Dynamic networks are also referred to as indirect networks. So if we have static interconnects, it connects the processors and memory by using point-to-point communication. How? Meanwhile, the dynamic networks, it uses switches and communication link to make the connection between the processors and memory. Okay, so this is the diagram that shows the differences between the static and dynamic network. So at the left side, okay, this one is the static network whereby it uses direct point-to-point communication between processor and memory. And this one, the right side, is the dynamic network which use switch and also the cable to make the connection between the processor and also the memory. Okay. All right. So switches that we use to communicate with processors and also memory map a fixed number of inputs to output. The total number of ports on a switch is the degree of the switch. So if we want to know how many switch that we need to use in the interconnection networks, we need to look at the total number of ports. So the cost of a switch grows as the square of the degree of the switch. Okay, so the peripherals hardware linearly as the degree, and the packaging cost linearly as the number of pin. All right. So how does the switches and the interconnection networks communicate? They are using network interface. Okay. So processors talk to the network via network interface. The network interface may hang off the I/O bus or the memory bus. So it's some like the network interface is the controller between the processors and also the network. Okay. So in physical sense, this distinguishes a cluster from a tightly coupled multi-computer. So the relative speeds of the I/O and memory buses will impact the performance of the network. So let's move on to the network topologies. There are many kinds of network topologies. Okay. These topologies trade off performance for cost. Okay. It might reduce the performance of the parallel computing or maybe increase the cost of constructing the network. So commercial machines often implement hybrids of multiple topologies for the reasons of packaging, cost, and available components. Okay. So the first topology is called buses. So buses can be found in Intel Pentium and also Sun Enterprise. Okay, it is the simplest and earliest parallel machines, okay, being used, and all processors access a common bus for exchange the data. So the distance between any two nodes is O1 in a bus. The bus also provides a convenient broadcast media. However, the major bottleneck for the bus is the bandwidth itself, how much the data is being carried by the bus. So typical bus-based machines are limited to dozens of nodes. Okay, so you have a bandwidth issue here if we are using a bus topology. So this is the diagram for the bus. A, bus with no local cache. B, bus with local or memory cache. With local memory or cache. Okay. So since much of the data accessed by a processor is local to the processor, a local memory can improve the performance of bus-based machines. So compared between A and B is better because B is using the local memory or cache. Okay, so the next one is called crossbars. Okay, a crossbar network uses a P multiply M grid of switches to connect P inputs to M output. This is the input, and then this is the output. Okay, processor and also the memory. Okay, in a non-blocking manner. So this is the switch that meets the processing and also the memory. Okay, so that's why we call it as crossbar. Okay, the cost of crossbar of P processors grows as P power of 2. So this is generally difficult to scale for large values of P. So Several examples that implement crossbar in the architecture is Sun Ultra HPC 10,000 and the Fujitsu VPP 500. Okay, so next one is multi-stage networks. Multi-stage network actually is being introduced to solve problems of crossbar and buses, whereby crossbar have an excellent performance scalability, but it's really poor cost scalability. And buses have excellent cost scalability, but poor performance scalability. So to improve these two weaknesses, so multi-stage interconnects strike a compromise between these extremes. So it's overcome these two limitations by providing another network topologies. Okay, so this is the diagram for multi-stage networks where the processors and memory are being connected together stage by stage based on the number of the processors and also the data that they want to pass. Okay. Okay, so another types of multi-stage is called as omega network. This is the most commonly used network. This network consists of log P stages where P is the number of inputs or output. So each stage at I, input I is connected to output J as shown at the following formulation. Okay. Okay, so this is an example of implementation multi-stage omega network. Each stage of the omega network implements a perfect shuffle as flow. So there are two types of shuffle, pass-through and also crossover. A perfect shuffle interconnection for it and input and output. So as you can see there, the shuffle or the message is being passed either by using pass-through or crossover approach. Okay, so pass-through actually is the straight line, or we call as the address of the source and destination is similar, so we need to use the pass-through. And crossover when the address of source and destination is not similar or different, so we need to implement crossover approach. Okay, so the perfect shuffle patterns are connected using 2 multiply 2 switches. The switches operate in two modes, either crossover or pass-through, which have been discussed earlier. Okay, so you can see here the pass-through approach and also the crossover. Okay, another example, a complete omega network with the perfect shuffle interconnects and switches. Okay, this one is connect between 8 inputs and 8 output. An omega network has P over 2 times log P switching nodes. So this is how we want to know the number of switching nodes that we need to apply. And the cost of such a network grows, okay, in the multi-stage omega network. Alright, so if we implement routing inside our multi-stage omega network, so let's consider the following situation. So let S be the source of the data and D be the destination of the data. So the data will traverse the link to the first switching node if the most significant bits of S and D are the same. So if the node, okay, or the address of the source and destination are the same, okay, choose the pass-through routine, or else if the address is not similar between the source and destination, so choose crossover routine. Okay, so this process is repeated for each of the log P switching stages. So each of the stages need to implement this kind of routine. So please note that this is not a non-blocking switch. Okay, there is no blocking or holding the operation during the parallel processing being executed. Okay, so this is how the switch or the data being passed through from the source and destination. Okay, an example from 010 destination, the source to destination 111, or 110 source to 100 destination. So it use crossover routine. Okay, however, it is being one of the message is blocked at the link A and B. Okay, this is an example of blocking in Omega network. Okay, next we have another network topologies called completely connected network. This is the counterparts of crossbar. Each processor is connected to every other processor. So the number of links in the network scales as OP power of 2, while the performance scales very well. The hardware complexity is not realizable for large values of P, and in this sense, these networks are static counterparts of crossbar. Okay, completely connected network. So next we have completely connected and star connected network. Okay, so this is how the complete connected network. This is how the complete connected network is being illustrated. Okay, all the processor being connected. Okay, without fail. Let's say if we have 8 nodes, all 8 nodes being connected together, and the right side is the star connected network. Not all the nodes actually are connected, but by using a central node. Okay, so there is a difference between complete connected and also star connected topologies. Okay, so let's look at the description for star connected network. So every node, as you can see before this, is connected only to a common node at the center. Center node is the controller to make the connection between the other nodes. So the distance between any pair of nodes is O1. However, the central nodes become a bottleneck because of what? All the available nodes, when they want to make a communication, they needs to ask, or they needs to go through to the center nodes. So that's why center nodes become a bottleneck. Okay, become traffic jam. So in this sense, star connected networks are static counterparts of buses. So let's move on to the next topologies, which are linear arrays, meshes, and KD meshes. So linear arrays means it has a linear line. Each node has two neighbors, either left or right. So let's say that line or nodes at either end are connected. So we can refer it to as 1D torus or a ring. Okay, so a generalization to two dimensions has nodes with four neighbors. Okay, we have north, south, east, and west. Further generalization to D dimension has node with 2D neighbors. So it grows the dimension, so it has more nodes, okay, to be constructed. So a special case of a D-dimensional mesh is called as hypercube. Okay, so D equals to log P, where P is the total number of the node. As the node become larger, so the mesh also become large, and it is called as hypercube. Okay, so this is the diagram of the linear array without wrap around link. So B is the linear array with wrap around link, where the end nodes is being connected with the first node. Okay, next one, 2 and 3 dimensional meshes. Okay, if consists more than one linear array, so it will become 2D. And then this kind of 2D has no wrap around. And then the B is 2D torus wrap around. It's still 2D, but it's a wrap around where the end node is connected together with the start node. Okay, this one, the C, is the 3D mesh, no wrap around. Okay. Alright, this is the special case of D-dimensional mesh. Okay, where it used log P just now to increase the nodes. So as you can see here, this is the 0D hypercube, 1D hypercube, 2D, 3D hypercube, and also 4D hypercube, which combines with another cube. Okay, so this is called as hypercubes and how it is being constructed. Alright, so let's look at the property of the hypercube. The distance between any two nodes, if there is a node and we want to know the distance, we need to look at calculate the log P. Each node has log P neighbors, and distance between two nodes is given by the number of bits positions at which the two nodes differ. So then we know the distance between the two nodes inside the hypercube. Okay, the next topology is called as tree-based network. There are two types of tree-based network, static and also dynamic. Okay, so static without using switch, and dynamic is using the switch. Okay, this is the switch. This is without switch. Okay, next one. Let's look at the property of tree. The distance between any two nodes is no more than 2 log P. So as you can see, links higher up, when we go higher up to the tree, the potentially carry more traffic than those at the lower level because of, if you can see the tree, it has only one node compared to the lower level has more than one nodes. So the nodes at the above level might carry more traffic than those at the lower level. So for this reason, a variant called a fat tree fattens the link as we go up the tree to improve or to overcome the more traffic in the upper levels of tree. So fat tree is being introduced. Okay, trees can be laid out in 2D with no wire crossing. So this is an attractive property of tree. Okay, so let's look at the diagram of fat tree. So we have one level here, one node here, but consists of more network to overcome the issue of data traffic. Okay, as you look at the lower level, okay, only consists of one interconnection network. Okay. Okay. So we already know several types of network topologies. So how we want to evaluate these topologies? So basically there are three factors need to be considered. The first one is called as diameter. Okay, diameter is we need to know the distance between the farthest two nodes in the network. And second one is bisection width, the minimum number of wire that you must cut to divide the network into two equal parts. And cost. the number of links or switches. Okay, how many links or switches that we need to use to make the connection between the nodes. So this is the summary on each topologies, how many diameter, bisection width, arch, connectivity, and also the cost that are required when we want to construct the parallel computing uh, according to the chosen network topologies. So this one is the for static interconnection network. Okay, this one for dynamic interconnection network. Okay, so the last subtopic is communication cost in parallel machine. So when the processor and memory passing the data, it's require them to communicate with each other. So actually in communication there is a cost or factors that influence the performance during the parallel processing. So instead of idling and contention limitation, communication also is a major overhead in the parallel program. So what are the factors that might cause the communication weakness? There are such as programming model semantics, either network topologies or in terms of data handling and routing, or even by looking at the software protocols that we use. Okay. Okay. So how to determine the message passing cost in parallel computers? So we need to look at the time. Okay, time is very crucial in the parallel computing. The total time to transfer a message over a network comprised of the following uh, timing measurement. The first one, we need to look at the startup time. Okay, the time spent at sending and receiving the nodes. Okay, executing the routing algorithm, the programming routers, and many more. And then we need to look at the per hop time. It is actually the time a function of number of hops and includes factors such as the data that need to hop from one processor to another processor. It has its latencies and maybe it has a network delays. Okay, the number three is per word transfer time, TW. This time includes all overheads that are determined by the length of the message. So the number of message that we need to pass also is need to be considered, because the longest or the largest or the bigger the size of the word, okay, we need more time to transfer the message, right? Okay, I think that's all for this chapter. So basically, we learn about the network topologies and also how to measure the topologies according to the several factors which have been discussed. Okay, so thank you all.